happy to meet the viewers of my YouTube channel in yet another module, Success to Gate Control Systems Module 17, which comprises problems in Nyquist Stability Analysis from different gate exam question papers. Let me straight away move on to the problem. Problem number 1 is taken from GATE 2017 Electronics Engineering set to question number 48. A unity feedback system is characterized by the open loop transfer function g of s equals 10k into s plus 2 by s cube plus 3s square plus 10. The Nyquist path and the corresponding Nyquist plot of g of s are shown in figures below. So two figures are shown. One is the Nyquist path, that is the Nyquist contour. The second one is the Nyquist plot of the g of s, that is mapping of Nyquist contour into g of s h of s plane. If 0 less than k less than 1, then the number of poles of the closed loop transfer function that lie in the right half of S plane is 4 options they have given 0, 1, 2, 3. So this particular problem, what is asked is, in the range of k, when it varies from 0 to 1, how many poles of the closed loop transfer function will lie in the right half of S plane? Now, by Nyquist stability criterion, we know very well that if the system has to be stable, then there should not be encirclement of the Nyquist plot about -1 plus j0 if there are no poles in the right half of S plane. Suppose there are some open loop poles which lie in the right half of S plane, then for the closed loop system to be stable, we should have as many anti-clockwise encirclements of Nyquist plot about -1 plus j0 as the number of right half of S plane open loop poles. Now, when k is greater than 0 less than 1, definitely this value minus k will be less than -1. For example, k is, let us say, 0.95. Therefore, this is minus 0.95. Therefore, -1 will lie outside this. And we can find that you have encirclement but not with respect to -1. Since there is no encirclement about -1 plus j0, we should take the number of encirclement as 0. Right. Now, we will see how many poles are there in the right half of S plane. And if we see s cube plus 3s square plus 10, if you factorize that, then minus 3.722 is one pole, 0.36 plus j 1.6, 0.36 minus j 1.6 are other two poles. So totally there are three open loop poles. Out of the three open loop poles, two open loop poles are present in the right half of S plane, that is these two complex poles. Therefore, if we apply the principle of argument, z minus p into minus 2 pi equal to n. So, p is equal to 2, that is number of open loop poles is 2. Z means zeros of 1 plus g of s, that is a closed loop poles. So, z minus 2 into minus 2 pi, since this k is less than 1, -1 is outside the Nyquist plot, therefore the encirclement is 0. Therefore, in order to have 0, z should be equal to 2. Then only 2 minus 2 into minus 2 pi is 0. That means 2 zeros of 1 plus g of s are present in right half of S plane. What do you mean by that? Two closed loop poles are present in right half of S plane. Therefore, option C fits into that. That is what concluded in the last statement. I hope you have understood this. So, it is just problem of mapping the number of encirclements given in the problem for the k specified, range of k specified, right? So, that mapping with the number of open loop poles in the right half of S plane. That's all. So, let us move to the next problem. So, this problem, the open loop transfer function of a unity feedback system is given by g of s, they have given pi into e to the power of minus 0.25s divided by s. In g of s plane, the Nyquist plot of g of s passes through the negative real axis at the point. They are given 4 options. So, this question is taken from GATE 2019 question paper, Electrical Engineering, question number 14. So, first let us write the sinusoidal transfer function, amplitude and phase angle. because we want to find out where it cuts the negative real axis. So where it cuts the negative real axis means that particular point phase angle should be made equal to minus 180. So we need phase angle, and we also need to find out that particular magnitude, that point. So let us first of all write the sinusoidal transfer function by putting s equal to j omega. So amplitude means pi is pi. E to the power of anything, e power j theta magnitude is cos theta plus j sin theta magnitude, which is equal to 1. E power j theta magnitude is 1 by mathematics. So pi into 1 divided by j omega modulus root of omega square omega. So amplitude is pi by omega. Then degrees. Pi is a scalar which is some radian. So it is a scalar, it is not an angle here. E power minus j theta means minus 0.25 omega is the angle. So minus 0.25 omega is in radians. Minus 0.25 omega is radians. Normally we express the phase angle in degrees. Therefore pi radians corresponds to 180 degree means minus 0.25 corresponds to what? Therefore minus 0.25 omega should be multiplied by 180 divided by pi. Okay, so that is as far as the numerator is concerned. Denominator j omega means tan inverse of omega by 0 tan inverse infinity 90 degrees, since in denominator minus 90 degree. That's all. So to find the frequency at which the Nyquist plot passes through the negative real axis, equate the phase angle to minus 180, because where it cuts the negative real axis, we know very well that the phase angle is minus 180. So equate this to minus 180. So minus 90, if it is brought to the other side, minus 90. So if we simplify this, omega is pi by 0.5. Pi is nothing but your 3.14 something. So divided by 0.5 is 6.28 radian per second. So therefore, this is the frequency at which the Nyquist plot cuts the negative real axis. Okay, but we want the point in rectangular form. So amplitude also let us find out. So we got the angle, amplitude let us find out. So amplitude is pi by omega. So pi by 6.28, that frequency 0.5. So 0.5 is the amplitude, phase angle is minus 180 because it cuts negative real axis. So 0.5 angle minus 180 is nothing but minus 0.5 plus j0, that is minus 0.5 comma 0. Therefore Nyquist plot passes through the negative real axis at the point minus 0.50. That's all. Option A is correct. See how simple the problem is. So this is how we have to do the problems in Nyquist stability analysis. Next problem. So it is just theory taken from GATE 2018 Electronics Engineering question number 5. The Nyquist Stability Criterion and Routh Criterion both are powerful analysis tools for determining the stability of feedback controllers. Identify which of the following statements is false. First statement, both the criteria provide information related to the stable gain range of the system. Yes, you can find out the range of stability in Nyquist as well as Routh. Yeah, it's correct only. The general shape of Nyquist plot is readily obtained from the Bode plot for all minimum phase systems. Yeah, when all the open loop poles and zeros are present in the right of a phase plane, definitely from the Bode plot we can get the Nyquist. Similarly, from the Nyquist also we can get the Bode. So general shape is obtained. This is also true. Routh criterion is not applicable in the condition of transport lag, which can be readily handled by the Nyquist criterion. Yeah, Routh criterion, because transportation lag means e power minus st. E power minus st, you cannot write the characteristic equation and solve, because you need characteristic equation to find out the stability using Routh criterion. In that case, e power minus st term you have to approximate. Therefore, you cannot use it properly. So, which can be readily handled by Nyquist criterion. Yes, that is what we have seen in the previous problem. In the previous problem, we have e power something. It is nothing but your transport lag. So, such a particular case also we can handle by Nyquist criterion. This is also true. Closed loop frequency response for a unity feedback system cannot be obtained from Nyquist plot. We can obtain from Nyquist plot gain margin, phase margin, all that we can. They are the closed loop frequency response measures. In fact, stability is also closed loop frequency response measure. So, closed loop frequency response cannot be obtained from Nyquist plot is false. So, option D is correct. That's all. Next problem. GATE 2018 Instrumentation Engineering question number 36. Consider the standard negative feedback configuration with G of s equal to this and H of s equal to this 1 by s. The number of clockwise encirclements of minus 1, 0 in the Nyquist plot of the open loop transfer function g of s h of s is dash. That is, they have given g of s as well as h of s, and they are asking how many encirclements will be made by the Nyquist plot of the loop transfer function g of s h of s about minus 1 plus j0. See, it is a second order system, very simple system. Of course, this denominator will have roots in the right half of S plane also, open loop pulse and right half of S plane also. And we have to find out the magnitude, angle, then omega 0, infinity, all that we have to do if we are using Nyquist stability criterion. The same problem, Nyquist plot problem, we can do it by Routh array. It is not that we should not use other forms, because we are asked to answer the question and we have to give the correct answer. That's all. We can use any method available in the world. Therefore, this problem can be easily solved with the characteristic equation. Because if you do the characteristic equation, 1 plus g of s h of s equal to 0. So you get, if when you simplify, you get this equation. So from this equation, if you try to use the Routh criterion, we know how to use the Routh criterion. So from the Routh criterion, what we can find out is, that is after formulating the Routh array and investigating the nature of the first column elements, we can find that there are two sign changes, positive to negative, negative to positive. So two sign changes means two roots of the characteristic equation. What is characteristic equation? 1 plus g of s equal to 1 plus g of s h of s equal to 0. That is zeros of the denominator polynomial, that is 1 plus g of s h of s, are in right half of S plane. So two sign changes means two roots are in right half of S plane. So that means system is definitely unstable. By principle of argument, we know z minus p into minus 2 pi equal to n. That is what we use in Nyquist stability criterion. Z, just now we have found out two zeros of 1 plus g of s h of s are present right half of S plane 2. And if you solve this particular denominator polynomial, that is g of s h of s, g of s h of s, that is 2 into s square minus 0.2s plus 100, because 1 by 2 is here. So if you solve that, so s square minus 0.2s plus 100, if you find out the roots, definitely we know 0.2 plus or minus square root of, so 0.2 plus or minus square root of b square minus 4ac, definitely we will have positive real part. So positive real part means, right? So positive real part means we have two open loop holes in right half of this plane. Why? Because 0.2 plus or minus square root of 0.2 square minus 400. Square root will be imaginary. Therefore, we will have 0.2 plus or minus j into square root of that divided by 2. So definitely this minus 0.1 plus or minus j something only. So why to waste time in finding the roots? So two open loop poles in right half of this plane, because positive real part, complex poles always occur in conjugate pairs. So 2 minus 2 into minus 2 pi is 0. That means we can find that there are no encirclements by this formula. Therefore, minus 1 plus j0 will not be encircled by the Nyquist plot. Therefore, number of clockwise encirclement is 0. Even if the question is number of anti-clockwise encirclement, it is 0. It is not at all encircling. Let us move on to the last problem. So it is taken from GATE 2016 Electrical Engineering Set 1. Question number 32. Loop transfer function of a feedback system is g of s h of s equal to s plus 3 by s square into s minus 3. Take the Nyquist contour in the clockwise direction. Then the Nyquist plot of g of s h of s encircles minus 1 plus j0. They have given 4 options. Anyway, I have shown two ways in which these problems can be solved. One is, even we can use the Nyquist stability criterion, or we can use the characteristic equation. You decide which method is easier. So this is the Nyquist contour, we know very well. So this is a straight line segment C1 varying from 0 to infinity. This is straight line segment varying from minus infinity to 0. This is an infinite radius arc, we know very well that. And here I have bypassed this portion because there are two poles at origin. Whenever two poles are present at origin, that means this particular straight line segment is passing through the singularity. Nyquist contour should never pass through the singularity. Therefore, to overcome the situation, we bypass this by a small, infinite small radius epsilon, and this is indented. So semicircular indent of infinite small radius is drawn to bypass the poles. And if you see this modeling of this is nothing but epsilon into e power j theta. This radius is epsilon. This angle is theta. So epsilon into e power j theta. Theta varying from here to here. Here means theta is minus 90. Here means theta is plus 90. Therefore, when the point is here, the angle is minus 90. When the point is here, angle is plus 90. So epsilon 0, theta varying from minus 90 to plus 90, we can use it. So if you see this particular loop transfer function, the open loop poles are present at 0, 0, 3 and minus 3. Therefore, one pole in right half of S plane. Since there is one pole in right half of S plane, for the system to be stable, there should be one encirclement, anti-clockwise encirclement. Let us see. This is the sinusoidal transfer function by putting S equal to j omega. Amplitude we know it is S plus 3, S minus 3 means it is an all pass transfer function. This alone S plus 3 by S minus 3. So it is 1 only. So 1 by omega square. That's all. So phase angle if you see, so 3 plus j omega phase angle is tan inverse of omega by 3. J omega square means phase angle 90 plus 90 180 because of the presence in the denominator minus 180. Minus 3 plus j omega means the point is in the second quadrant. Therefore, this tan inverse of omega by 3 should be subtracted 180 minus. That's all. Therefore, 180 minus 180 is minus 360 plus 2 tan inverse of omega by 3. So minus 360 plus 2 tan inverse of omega by 3 is the phase angle. Okay, now we have seen the amplitude and the phase angle. Now we will have to map this also, we have already seen, because there are two poles at origin. So as epsilon tends to 0, theta varying from minus 90 to plus 90 for this small radius, that is epsilon e power j theta. So here S is put as epsilon e power j theta 3 plus S epsilon e power j theta, S square epsilon e power j theta whole square minus 3 plus S means minus 3 plus epsilon e j theta. Now as epsilon tends to 0, what happens is this is 0, this is 0. So 3 by minus 3 is minus 1. So minus 1 means what? What do you mean by minus 1? Minus 180 degree, because one angle minus 180 is minus 1. So for that one angle minus 180 I have put, right. Then epsilon square e power j theta, e power j2 theta, as epsilon tends to 0, 1 by 0 will become infinity. So magnitude becomes infinity. E power j2 theta means angle is 2 theta because of the presence in the denominator. Minus 2 theta, that's all. So here 1 minus 2 theta, and because of the 3 by minus 3 minus 1 here, another minus 180. So angle is minus 180 minus 2 theta. Therefore, what happens is, as epsilon tends to 0, theta varying from minus 90 to plus 90, the infinite small semicircular indent, that is small circular indent, is mapped onto infinite arc radius. I have already told in the Nyquist Stability Control System lecture series, what I have told is, when you map a big thing in Nyquist contour, infinite arc radius is mapped onto origin if the number of open loop poles is greater than the number of zeros. Similarly, that infinite arc radius is mapped onto a constant if the number of open loop poles is equal to number of open loop zeros. See here, infinite small radius is mapped onto infinite radius. That means, so here few points that will be mapped to many points. Earlier, these are many points in S domain mapped into origin or constant. So that is the beauty of the mapping from Nyquist contour to G of S, H of S contour, especially at this singularity. So infinite small semicircular indent is mapped onto infinity. So as theta varying from minus 90 to plus 90, minus 180 minus 2 theta varying from 0 degree, actually minus 180 minus 2 into theta minus 90 means 0 degree. At plus 90 degree, minus 180 minus 2 theta, it will be minus 2 into minus 90, so minus 90 plus minus of 180, because theta is 90 degree, so infinity angle minus 360 degree. Therefore, you have infinite small semicircular indent mapped onto infinite arc radius with angle varying from 0 to minus 360 degree. That means a complete circle with infinite radius. That's the meaning. At omega equal to 0, what is g of j omega or g of j omega, h of j omega? Right, so g of j, here you have to put h of j omega also. So g of j omega, h of j omega is infinity angle minus 360 degree. How? 1 by 0 is infinity, infinity. At omega equal to 0, what happens? This is 0, so minus 360 degree. Omega equal to infinity, the magnitude is 0, 0. So what about the angle? Here you'll have infinity, tan inverse of infinity means 2 into 90, so 180. So minus 360 plus 180 is minus 180. So this is the mapping. Let us see how to draw this. So this is the Nyquist contour. So mapping of C1 is nothing but your normal polar plot. So mapping of C1 polar plot means infinity angle minus 360 to infinity angle minus 180. So this is the mapping of the polar plot because 0 to infinity. So 0 to infinity, of course 0 is indented, bypassed. So infinity angle minus 360 to infinity angle minus 180. So this is infinity. So I have assumed this as infinity. So infinity angle minus 360 to 0 angle minus 180. So this is your minus 180. So actually this infinity I cannot show it on a finite dimension plane. So I have made this radius as infinite radius. That's all. This entire thing is infinity. This entire from here to here is infinity. That's all. Okay. So this is mapping of C1. Right, that is this. What is next? We have to map C3. We know very well that whenever the number of open loop poles is greater than the number of zeros, always it is mapped on to origin. This we know, I have already explained in the control systems lecture series, so I don't want to repeat this. Always this is mapped on to origin if the number of open loop poles is greater than the number of open loop zeros. Therefore, this is mapped on to origin, right? Then this mapping I want. So this is actually mirror image of this. So this you take mirror image, that's all. So direction, this direction, so this direction, then this to this, so this to this, that's all, because this is origin here. Right, now we have to map one left out portion, that is this infinite small arc radius. What is infinite small arc radius? We know it is mapped on to infinity angle 0 to infinity angle minus 360 degree. So this is infinity angle 0 degree. This touches 0 degree at infinity to infinity angle minus 360. What is infinity angle? This touches this particular real axis at infinity, 0 degree, that's all. So we can definitely find that minus 1 plus j0 will be in between because it covers the entire negative half of the this portion. Therefore, if you see, there is one clockwise encirclement. If you see the direction, so I hope you have understood how I have marked the direction. Here to here, that is here to here. Here to here, that is origin. Here to here, that is this. Here to here, that is this. Therefore, there is one clockwise encirclement about minus 1 plus j0. That is why Nyquist plot encircles minus 1 plus j0 once in clockwise direction. The question is not whether the system is stable or not. Of course, the same problem we can do it in a very simple manner if we use this alternative approach. We know the characteristic equation because we know g of s, h of s. This is s plus 3 by s square into s minus 3. So find out 1 plus g of s, h of s. So form the characteristic equation. After forming the characteristic equation, formulate the Routh array in the same manner. And if we formulate the Routh array and find out the coefficients, we can find that there are two sign changes. Two sign changes in the first column of the Routh array means two roots of the characteristic equation, that is two roots of 1 plus g of s, h of s are present in right of s plane. That means this z is equal to 2. Z means zeros of 1 plus g of s, h of s. So z minus p into minus 2 pi equal to n. So this z is 2, right? So 2, because two roots of characteristic equation present right of s plane, because two sign changes, and one open loop pole in right of s plane because s equal to 0, s equal to 0, s equal to 3. So if that we have already said s equal to 3, there are s equal to 0, 0, 3, minus 3. Of course, I should not take this this minus 3. This minus 3 is not at all there. Why this minus 3 is not there? Because this minus 3 is actually 0. Maybe I can say 1 0. I can annotate. Here I can write 1 0. 1 open loop 0. That's all. 1 open loop 0. So this is open loop poles at this and 1 open loop 0 at this point. 1 open loop 0 at this point. That is open loop. This is, yeah, 1 open loop 0. That means I will write in short form open loop 0. So actually this is not at all required. This open loop 0 is not at all required for our conclusion, because we are comparing only the open loop poles and the zeros of 1 plus g of s Java. Since I have written, I have taken this point into consideration. That's all. So going back, yeah. So z minus p into minus 2 pi is n. So 2 minus, so 2 zeros, only one pole in right half of plane. So 2 minus 1 into minus 2 pi is 1 minus 2 pi is minus 2 pi. Minus 2 pi means negative 360 degree. Negative 360 degree means 1 clockwise encirclement of g of s h of s contour about minus 1 plus j0. That's all. So option A is correct. So what is option A? Option A is 1s in clockwise direction. See, this much tedious problem has been simplified into a normal Routh array problem. That's all. So that is the beauty of understanding the problem and doing it. So here again, I just wanted to justify that I have never used any new formula, new expression, new concept. Whatever concepts that I have already explained in my regular control system lecture series 1 to 23, that only I have used. If you have still doubts, you please go through this video and this video. First and second problem I have made use of only this video. Third and fourth and fifth I have made use of the concepts in Routh Hurtwitz as well as Nyquist criterion, because for simplicity I have used that also. You would have seen in last three problems. So if you have still doubts, you can post your comments, queries or feedback to this mail ID. You can WhatsApp to this number, and these two videos you can refer these two URLs, that is this and this. The same thing is put here also. So I thank you very much for your views, subscriptions and sharing. I need more views, more subscription and more sharing, so that the learning community will be benefited to a greater extent. So I will meet you in the next module. In that also, that is module 18, I will cover the left out problems from GATE examination question papers 2015 to 20, covering polar and Nyquist stability analysis. So till I meet you in the next module, thank you and goodbye.